Okay, so sixth period, you're going to grab the sheet on the front counter and you're going to staple it to your notes. We're going to do a couple practice problems. When you're ready, we'll start. Ninth period, you're just going to take that last sheet from the notes off and throw it out, recycle it, and then you're going to staple the new sheet instead. So we're doing different practice problems. Okay guys, we're going to look at the practice problems at the end of the notes. You should have grabbed a new sheet and either got rid of the old sheet if you're ninth or just stapled it to the notes if you're in sixth. So here's our first practice problem. Find the frequency and color of the light emitted by a hydrogen atom as the excited electron falls from the third to the second energy level. So the first thing we're going to have to do is we're going to have to look at our reference table at page 3. Let's see. Okay, so we're looking here on page 3. We got the energy levels of hydrogen. We're going from the third N3. Okay, so that's negative 1.5 eV. And what that really means is that, okay, we're going from this negative 13.60 eV. So we have this much energy that we have to overcome to fully remove the electron, to ionize it. Okay, but to get from this ground state to this ground state here, 2 and 3, if we do subtract these two values from each other, we find out the amount of energy it takes to get from the ground state to N3. Remember, it's discrete or quantized energy, so it's a precise amount of energy. If you don't get that exact amount of energy, the electron won't gain any energy at all, and no light will be given off. Okay? So for this problem, we've excited our electron up to the N3. It's then going to fall back down, and the energy that's release is going to be released as a photon with a specific wavelength. Okay, so we're going from N3 to N2. So our initial energy is negative 1.5 eV. Our final is going to be negative 3.4 eV. Excuse me. We're going to use the equation on page 5, or two equations eventually. So we're going to start out with this one. We got the E photon. E photon equals E initial minus E final, and then we're going to make use of this equation because we can set them equal to each other. Okay. So our first given, our E initial, let's try that again. Our E initial is equal to our negative 1.51 eV. Our E final is equal to negative 3.4 eV. Our equation is E photon is equal to our E initial minus our E final. So if we sub that in, I'm just going to abbreviate a little bit. And we have to remember to put the smaller number first. First off, because it's falling, and because we have negative numbers, we want to end up with a positive energy. Okay. So if we do that out, you end up with 1.89 eV. Okay. So that's the first step of getting the EV. But if you look at your reference tables, and we're trying to ultimately find the frequency. So if we look at our reference tables, okay, we go to the very first page. If we look at Planck's constant, okay, if you notice that energy unit is in joules, okay? So in our chart on page 3 is in EV, so we have to change from electron volt to joules. Well, if we look right here, Stop being annoying. Okay, if we look right here, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Okay, so we can make that unit conversion. We just take our 1.89 and we multiply it by 1.6 times 10 to the negative 19 joules. Okay? I'll give you guys a second to write that down, and then I'm going to go to the next tab. Okay, so if you do that out, you get an energy level for the E photon in joules, which is equal to 3.024 times 10 to the negative 19 joules. Okay, so now we found the joules. Okay, and why do we do that? Well, the question is looking for the frequency and the color. Okay, and the Planck's constant on the front of the reference tables is in joules per second, so we have to convert our EV, which is a form of, or is a unit for energy, to joules. Okay, the equation we're looking to use is E photon is equal to HV. And when we find that frequency, we can use our reference tables, the inside cover. Okay, we can use. Then we can solve for the frequency and see what color the photon is. Okay. So we know that value now. So it's 3.1, just to make sure. Why are we freezing? Get that right, please. Okay, apparently they hate me. There we go. So, then we can get our H from the front of our reference tables at 6.63 times 10 to the negative 34 joules per second. Okay? And then we can solve. I'm going to rearrange this. Okay, so solve for F, so divide by the H, so we get the frequency is equal to our E photon divided by our constant. So we have frequency is equal to our 3.024 times 10 to the negative 19 joules. We get our Planck constant. So we get a frequency. There we go, it's a little bit better. It's going to drive me crazy. We get a frequency equal to 4.56 times 10 to the 14th hertz. Okay? I'll give you a second to write that down. Or you can pause the video, that works too. So if we go, where am I going? Here, okay, we're looking at our electromagnetic spectrum. Our answer is 4.56, so it's actually between this one and this one. And that one, close enough, you know what's happening. And that means that it is a red, the color of the photon would be red, okay? So if we had a whole bunch of hydrogen gas and we were able to hit it with, if we were able to excite the electrons in the hydrogen and they would drop back down, we'd be able to see this red spectrum, and we'll actually we'll observe that on Tuesday. Now what I want you guys to do is I want you to move on and try the second practice problem. Oh, before that, I want to show you something. Okay, so the idea here is that there's a couple different series with hydrogen based on what kind of light is emitted. So there's a Lyman series, which means that all the light emitted at the change of these levels is in ultraviolet. We don't need to know that it's called the Balmer series, but the one we deal with is the Balmer series. So it only ever drops to the second energy state. So the electron gets excited. So for example, if we go from the third energy level to the second energy level, the photon that's going to be emitted is a red light. Okay? So if we're going from this third one to the second one, a photon of red light is going to be emitted. If we're going from the fourth to the second, it's a green color. If we go from the fifth to the fifth to the second is a blue color. And then if we go from the sixth to the second, it's a purple color, violet. And then the very last one, it's very hard to see. It's pretty much in the ultraviolet. Going from the seventh to the second gives an ultraviolet. So that's the idea. When we drop from these energy levels, light's going to be emitted. And light's emitted every time we drop from one level to the next. It's just sometimes we can't see it because it's not part of the visible spectrum. Okay? So what I want you to do now is do the second practice problem, find the frequency and color of the photon emitted by a hydrogen atom as excited electron falls from the fifth to the second energy level. Remember that you always do E initial minus E final. And then you got to convert your EV to joules. And then you use the E photon equals H frequency to find the frequency. Or actually, the E photon equals H times F to find the frequency. And then I'll put the answer up on the board in a second. Just pause the video here and then play it again when people have completed the practice problem, and we'll move on to the next one. Okay guys, for this you should have got an answer for the frequency of 6.9 times 10 to the 14 hertz, which if you look at your reference tables is a violet light. Okay, so we're going to move on to the next practice problem. I'm just going to set it up for you guys, and then you're going to take it from there. Okay, so find the frequency and color of the photon emitted by a mercury atom as its excited electron falls from the F level to the D level energy level. So a couple things. First off, they just use, instead of numbers, they use letters. It's just to signify that it's a different atom. Remember from the video in our talk yesterday that different atoms have different, their electrons get excited to different energy levels, and that's why they give off different light. Okay, you can think of it in terms of the video, the different energy steps. So the hydrogen atom, its electrons are going to have different energy steps than our mercury atom. And those steps, those differences between those steps is how much energy gets put into the photon, and that's going to dictate, that amount of energy is going to dictate our frequency, our wavelength. Okay? So if we go back to our reference tables, okay, and we look once again at the spectrum. This time we are just going, instead of number levels, we're using letter. So we're going from the F. From the F. One more time. All right, you know where the F is. You can see it. I don't know why it's not highlighting. And then, so that would be negative 2.68 going down to the D. Okay. I'm not going to worry about it. So going down here to the D. Okay, and it's similar to the hydrogen atom. That going from like J to I will give off light. Going from H to E will give off light, going from F to B will give off light, but all those are in the non-visible. The only changes in energy level that will give you a visible photon are dropping from higher levels down to D, okay? Like with our hydrogen, it was dropping from higher levels down to our number 2, okay? So, in this one, we're going from our F level down to our D level, okay? So we're looking at our F level, our E initial, is equal to negative 2.68, our E final is equal to negative 4.95. Okay? And you're going to use the same equation, solve it the same way. Okay? So I'll let you take it the rest of the way, and then once everyone's kind of finished with that problem, you can go forward a little bit, and I will give you the answer with the frequency and the color.